In the year 820 CE, in the great city of Baghdad, a Persian scholar sat down to write a book that would change mathematics forever. The book's title was lengthy, The Compendious Book on Calculation by Completion and Balancing, but its impact was anything but compact. This single work would give birth to an entirely new branch of mathematics, algebra, and its author's name would become so famous that it would eventually transform into a word we use thousands of times daily. Algorithm. The scholar was Muhammad ibn Musa, Al-Khwarizmi, and while Europe was struggling through its dark ages, Al-Khwarizmi and his colleagues in the Islamic world were preserving, translating, and revolutionizing mathematics in ways that would shape human knowledge for the next 1,000 years. Welcome to Maths Whisperer, where we uncover the hidden stories of mathematics. I'm your host, and this is Season 2, Episode 7. Today, we're entering the House of Wisdom in Baghdad to discover how Islamic scholars became the bridge between ancient mathematical traditions and modern mathematics, and how one brilliant Persian mathematician gave us the tools to solve problems that had stumped humanity for millennia. To understand Al-Khwarizmi's achievement, we need to understand the world he lived in. The 8th and 9th centuries CE witnessed one of history's great intellectual flowerings, the Islamic Golden Age. While Western Europe had fragmented after Rome's fall, the Islamic world was unifying under the Abbasid Caliphate. The capital, Baghdad, founded in 762 CE, quickly became the world's largest and most cosmopolitan city. Scholars, merchants, and travelers from Africa, Asia, and Europe converged there, bringing knowledge from diverse civilizations. The Abbasid Caliph, Al-Mu'min, established the Bayt al-Hikmah, the House of Wisdom, around 830 CE. This wasn't just a library, it was a research institute, translation center, and academy all combined. Scholars were paid to translate texts from Greek, Sanskrit, Persian, and other languages into Arabic. Mathematicians, astronomers, physicians, and philosophers worked together, sharing ideas across cultural and linguistic boundaries. This was intellectual cross-pollination at its finest. Greek mathematics met Indian arithmetic. Persian astronomy encountered Egyptian geometry. Chinese innovations mixed with Babylonian traditions. And from this fertile meeting of minds emerged new mathematical insights that surpassed any single tradition. Al-Khwarizmi arrived in Baghdad around 810 CE. We know little about his early life. He was born in Khwarizm, a region south of the Aral Sea in modern-day Uzbekistan, hence Al-Khwarizmi, meaning from Khwarizm. He was Persian, Muslim, and extraordinarily talented in mathematics and astronomy. At the House of Wisdom, Al-Khwarizmi had access to texts from across the known world. He studied Greek mathematical works, particularly Euclid and Diophantus. He learned Indian arithmetic and the decimal Placeval system. He examined Persian astronomical tables and Babylonian algebraic methods, and from this synthesis of knowledge, he created something new. Around 820 CE, Al-Khwarizmi wrote al-Kitab al-Mukhtasar fi Hisab al-jabr wal-muqabala, the compendious book on calculation by completion and balancing. The words al-jabr and al-muqabala referred to specific techniques for solving equations. Al-jabr meant restoring or completing moving terms from one side of an equation to another. Al-muqabala meant balancing simplifying equations by combining like terms. When this book was eventually translated into Latin centuries later, The word al-jabr became al-jabr. An entire branch of mathematics took its name from Al-Khwarizmi's Arabic term. But what made this book revolutionary? After all, people had been solving equations for millennia. The Babylonians solved quadratic equations. The Greeks worked with geometric algebra. The Indians and Chinese had algebraic methods. Al-Khwarizmi's genius was systematization. He didn't just solve equations, he created a general method that worked for entire classes of equations. He organized equations by type, showed systematic solution procedures, and explained why these procedures worked. Let me walk you through Al-Khwarizmi's approach, translating from his geometric language into modern notation so you can see what he accomplished. Al-Khwarizmi classified equations into 6 basic types, based on the terms they contained: constants, numbers, roots, what we'd call x, and squares, what we'd call x squared. The 6 types were squares equal roots, squares equal numbers, roots equal numbers, squares and roots, equal numbers, squares and numbers, equal roots, roots, and numbers equals squares for each type. He provided a systematic solution method. Let's look at type 4, the most interesting: squares and roots, equal numbers. In modern notation, this is x squared plus bx equals. Al-Khwarizmi's method was geometric, but translates to our quadratic formula. He would say, take half the coefficient of the roots, square it. Add this to the number, take the square root of the result, and then subtract half the coefficient of the roots. Sound familiar? It's the quadratic formula, but expressed in words and justified geometrically rather than algebraically. Here's a specific example he gives. A square plus 10 roots equals 30-9. In modern notation, x squared plus 10x equals 39. His method: take half of 10, that's 5, square it 25, add 239 64, take the square root 8, subtract 5. Answer: 3. Check it. 3 squared plus 10 times 3 equals 9 plus 30 equals 39. Correct. What's remarkable is that Al-Khwarizmi didn't just give recipes, he explained why they worked using geometric proofs. He drew squares and rectangles to show that his algebraic manipulations made geometric sense. This provided rigorous justification, connecting the new algebra to established Greek geometric methods. He also worked out practical applications. The book contains problems about inheritance, division, land surveying, commerce, and engineering. Al-Khwarizmi showed that abstract algebra solved concrete problems, making mathematics useful for judges, merchants, architects, and administrators. This practical emphasis was characteristic of Islamic mathematics. It wasn't pursued only for intellectual beauty, though. That mattered too, but as a tool for solving real problems in a complex, sophisticated civilization. But Al-Khwarizmi's contributions went far beyond algebra. He wrote another influential book around 825 CE on the calculation with Hindu numerals. This book introduced the Indian decimal place value system to the Islamic world, and eventually to Europe. The Latin translation of this work began Dixit, Al-Khwarizmi, thus spoke Al-Khwarizmi. European scholars started calling arithmetic procedures using the decimal system algorithm after Al-Khwarizmi's name. Eventually, this evolved into our modern word, algorithm, any systematic procedure for solving a problem. Think about that. Every time you talk about computer algorithms, search algorithms, encryption algorithms, you're honoring Al-Khwarizmi. His name became synonymous with systematic mathematical thinking. Al-Khwarizmi also made major contributions to astronomy. He wrote astronomical tables, called CE, that corrected and extended earlier Greek and Indian work. He calculated the positions of the sun, moon, and planets with impressive accuracy. These tables were used throughout the Islamic world and eventually in Europe. He worked on geography, creating an improved world map based on Ptolemy's geography, but with corrections from Islamic travelers and traders who had explored further than any Greek. His map included more accurate positions for cities, rivers, and coastlines across Africa, Asia, and Europe. He studied timekeeping, developing methods for calculating prayer times at different latitudes, practical need for Islamic religious observance that required sophisticated trigonometry, and astronomy in every field Al-Khwarizmi touched. He synthesized existing knowledge from multiple traditions and added his own innovations. He was the epitome of the Islamic Golden Age scholar, multilingual, interdisciplinary, building bridges between civilizations. But Al-Khwarizmi didn't work alone. The Islamic Golden Age produced an extraordinary constellation of mathematical talent. The Banu Musa Bros Muhammad Ahmad and Al-Hasan worked at the House of Wisdom alongside Al-Khwarizmi. They translated Greek mathematical texts, studied mechanics and geometry, and developed ingenious automated devices that anticipated later engineering. Sabit ibn Qurra, a 9th century mathematician, translated Euclid, Archimedes, and other Greek mathematicians into Arabic. He also made original contributions to number theory, discovering what are now called Thabit numbers. He worked on infinitesimal geometry, anticipating some ideas that would later appear in calculus. Al-Khwarizmi, in the 10th century, extended Al-Khwarizmi's algebra to include operations with polynomials. He could add, subtract, multiply, and divide algebraic expressions, moving toward what we'd recognize as modern algebra. Omar Khayyam, famous in the West as a poet for his Rubaiyat, was actually a brilliant mathematician. In the 11th century, he wrote a treatise on algebra that went far beyond Al-Khwarizmi, tackling cubic equations. He couldn't solve them. Algebraically, that wouldn't be accomplished until the Renaissance. But he solved them geometrically using conic sections. Al-Khwarizmi, and later Ibn al-Haytham, worked on problems in optics and geometry that required mathematical techniques anticipating calculus. They calculated volumes of solids of revolution, areas under curves, and worked with infinite series. Nasir al-Din al-Tusi, in the 13th century, wrote extensively on trigonometry, essentially creating it as an independent mathematical discipline separate from astronomy. His work was so influential that it affected Copernicus centuries later. Throughout this period, from the 8th through 14th centuries, Islamic mathematicians were at the forefront of mathematical knowledge. They preserved Greek mathematics that would have otherwise been lost. They transmitted Indian arithmetic to Europe, and they made original contributions that advanced mathematics beyond what any previous civilization had achieved. The transmission of this knowledge to Europe is a fascinating story in itself. Islamic Spain, Al-Andalus, became a crucial bridge. Cities like Cordoba, Toledo, and Seville were centers of learning where Christian, Jewish, and Muslim scholars worked together. Libraries in these cities held Arabic translations of Greek texts that had been lost in Christian Europe. When Christian kingdoms gradually reconquered Spain during the 11th through 13th centuries, they discovered these libraries. European scholars, realizing the mathematical wealth they contained, began translating Arabic texts into Latin. Gerato Cremona, in 12th century Toledo, translated over 70 Arabic works into Latin, including Al-Khwarizmi's Algebra and Euclid's Elements from an Arabic translation. Since the Greek original was unavailable in Europe, Robert of Chester translated Al-Khwarizmi's Algebra into Latin in 1145. This translation introduced the word algebra to Europe and showed European mathematicians systematic methods for solving equations. Leonardo of Pisa Fibonacci learned Arabic mathematics during his travels in North Africa. His 1202 book, Liber Abasi, introduced European merchants and scholars to Indian Arabic numerals and algebraic methods. Fibonacci explicitly acknowledged his debt to Arabic mathematics. Through these translations and transmissions, Islamic mathematical knowledge flowed into Europe. Just as European universities were being established and European scholars were hungry for new knowledge, the impact was transformative. European mathematics in the 13th through 15th centuries was essentially learning and absorbing what Islamic mathematicians had accomplished centuries earlier. The Renaissance in mathematics was largely about recovering and understanding knowledge that the Islamic world had preserved and extended. Consider what would have been lost without Islamic scholars. Most Greek mathematical texts survived only through Arabic translations. Euclid's Elements, Ptolemy's Almagest, works by Archimedes, Apollonius, and others, the Arabic versions, kept them alive when Greek originals disappeared. Indian mathematics, the decimal system, trigonometric methods, algebraic techniques reached Europe through Arabic intermediaries. Without Islamic transmission, Europe might never have adopted the decimal system, forever handicapping European mathematics and the original contributions algebra as a systematic discipline, advanced trigonometry, sophisticated astronomical tables, improvements in geometry. These Arabic innovations became foundations for later European mathematics. The European Renaissance in mathematics, science, and astronomy was built on Islamic foundations. Copernicus used Altusi's astronomical work. Renaissance algebraists built on Al-Khwarizmi and Omar Khayyam. Kepler and Galileo benefited from centuries of Islamic astronomical observations and theories, yet this contribution is often minimized or forgotten in standard histories of mathematics. The narrative often jumps from Greek mathematics to European Renaissance, as if nothing important happened in between. Islamic mathematicians are relegated to being mere preservers and transmitters, not innovators. This is historically inaccurate and unfair. Islamic mathematicians were crucial innovators who advanced mathematics far beyond what they inherited. Al-Khwarizmi didn't just preserve Greek algebraic, created a new, more powerful algebraic framework. Islamic trigonometry surpassed anything the Greeks accomplished. Islamic decimal arithmetic made calculation vastly more efficient than Greek methods. The Islamic Golden Age represents one of history's great intellectual flowerings, and mathematics was at its heart. Why did this Golden Age end? The reasons are complex: Mongol invasions, political fragmentation, economic changes, shifting trade routes. The sack of Baghdad by Mongols in 1258 destroyed the House of Wisdom and killed countless scholars. Islamic civilization continued, but its scientific golden age gradually declined. By the time Europe was entering its scientific revolution in the 16th and 17th centuries, the center of mathematical innovation had shifted westward. But the tools European mathematicians used: algebra, decimal arithmetic, trigonometry, improved astronomy, all bore the stamp of Islamic mathematical achievements. Today, Al-Khwarizmi's legacy surrounds us. Every algebraic equation you solve uses methods he systematized. Every algorithm you encounter bears his name. The decimal arithmetic you perform daily came to Europe through his work, yet most people have never heard of him. He's not taught in schools alongside Pythagoras or Euclid. His name doesn't appear in popular culture. His achievements are known mainly to historians and mathematicians. This needs to change. Al-Khwarizmi deserves recognition as one of history's most influential mathematicians. His work touched billions of lives across centuries. Modern mathematics, computer science, and engineering rests on foundations he helped build. The Islamic Golden Age more broadly deserves recognition as a crucial chapter in human intellectual history. It wasn't a mere intermission between Greek and European mathematics. It was a vibrant, creative period that advanced human knowledge immensely. And the lesson for today is clear: knowledge flourishes when cultures meet and exchange ideas. The House of Wisdom brought together Greek, Indian, Persian, and Arabic knowledge. From this synthesis came innovations greater than any single tradition could produce. In our globalized world, we have unprecedented opportunities for intellectual exchange. Scientists and mathematicians collaborate across continents. Knowledge spreads instantly online. We're living in a new golden age of cross-cultural, intellectual fertilization. But we must remember and honor the past examples. The Islamic Golden Age shows what's possible when societies value knowledge, support scholars, translate and preserve texts from other cultures, and create spaces where diverse traditions can meet and synthesize. So next time you solve an algebraic equation, remember Al-Khwarizmi in Baghdad, systematizing methods that would shape mathematics for a millennium. Next time you use an algorithm, remember that you're honoring a Persian mathematician whose name became synonymous with systematic problem solving. And remember that mathematics is truly global, built by Greeks, Indians, Chinese, Mayans, Arabs, Persians, Europeans, and countless others, each contributing to the edifice of human knowledge. If you're fascinated by how mathematical knowledge traveled across civilizations and how Islamic scholars bridged ancient and modern mathematics, subscribe to Maths Whisperer. We're releasing daily episodes exploring mathematical thinking across cultures and time. Tomorrow, we're meeting John Nash and exploring game theory, how one brilliant mathematician's insights into strategic thinking revolutionized economics, biology, and our understanding of human behavior. Hit subscribe, ring that bell, and comment. What other Islamic Golden Age achievements would you like to learn about? Let's keep exploring mathematics together, one whisper at a time.